We've all seen Newton's laws at this point, but let's do a quick recap just in case. Newton's first law says every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. What you need to know is that a static system doesn't accelerate. It's important because a lot of times we think of static systems as being stationary, and that's not quite it. We can be moving as long as we're moving at constant velocity. Newton's second law says that force is equal to the change in momentum per change in time. For a constant mass system, this means that force is equal to mass times acceleration. If it's not accelerating, a static system, that means that the sum of forces must add to zero. I do want to point out here, this is the vector sum, which means the forces in all of the directions have to add to zero. And lastly, Newton's third law tells us that for every action, there is an equal and opposite reaction. This is important because what it implies is that we have applied loads. That's what we've been looking at so far when we do things like come up with the resultant force of all the forces that are being acting on our system. And we know that if the sum of forces is equal to zero, these applied loads have to, equal and opposite reaction, be equal to what are now going to be called the reaction forces. So this is a fancier way of saying the sum of forces is equal to zero, but it also brings about a new possibility that we need to make sure we acknowledge, and that is that if we have some system and acting on that system are a collection of loads, a collection of forces, the thing that this last law tells us is equal and opposite reaction. If we want the sum of forces to equal zero, there are going to be unseen reaction loads, reaction forces, and possibly reaction moments that hold our system in place. And when I say in place, I mean static, so either in uniform velocity or stationary. In general, there are three possible responses to an applied load: equilibrium, deformation, and acceleration. Equilibrium is the focus of a statics course. And what it is that ma is equal to zero. In other words, we have particles and we have rigid bodies, and they don't accelerate. So the forces have to balance, the moments have to balance, and everything sums to zero. Deformation is a relatively small amount of motion in which the object changes shape in response to an applied load. This is how the real world works and where you're headed next. So in deforms class, deforms, sometimes it's also called solids or solid mechanics class, you'll talk about this, and what it is you're going to look at finite motions so that the system changes shape and comes to a new equilibrium configuration. So it'll still come to equilibrium, it just won't be in the same shape that it used to be. And lastly, we have acceleration, in which there are unbalanced forces, and so now the entire system accelerates, and it won't stop accelerating until new forces are introduced that restore equilibrium at some new state, and that is the topic of dynamics class. What's fun is, in order to do deformation and acceleration, we have to start with understanding equilibrium. This is where we're going to learn how to draw free body diagrams, apply force and moment balances, and then as you move on, what you're going to see is we're just going to change the other side of the equation. So we've been looking at things, we're going to be looking at things that are the sum of forces equal to zero, and in deforms and acceleration, we're just going to monkey around with the right side of this equation, but the left side you're already going to be comfortable with.